Base dissociation constant, also known as Kb. Now what is this? It is the equilibrium constant, like what we've been dealing with KEQs. So it is the equilibrium constant, but for the ionization of a base, not for an acid like we've been looking at with Ka. Now, it's pretty much similar to weak acid problems that we've been working on recently in the previous videos. So it's similar to weak acid problems. I'm just going to be putting here in brackets, just assume that the hydroxide concentration is only from the base. Let me give you an example here. So if we have NH3 and we add it with water so that it dissolves, it's going to have a reversible reaction and it's going to create NH4. Why is it going to be NH4? Because we added an extra proton onto this NH3. Where did it come from? Well, it came from this H2O. So if this one left, right, so we deem this one here as kind of the acid in this case, and this here is going to be the base in this case, because we know that bases are proton acceptors. If it accepts that, then it's going to become 4, okay, instead of 3. Now, because we have an extra proton, it becomes a little bit more positive, hence we have that positive symbol representing it as the cation. And then what's going to happen here? Well, this one lost, right? It donated that proton, so there's only going to be one H as opposed to two H's over here, and then this becomes our anion over here. Now, we always assume that this OH concentration is coming from this base. Now, what does it mean here? Again, the OH concentration is only from the base, because in previous grades you probably have learned that with an NH3, okay, how can this NH3 create an OH minus? Because you were led to believe that a base was pretty much just a release of hydroxide, and there needs to be a hydroxide in the actual reactant, okay? But obviously there is no hydroxide in the reactant here, but we still have a hydroxide that has been yielded, okay? So even though we have a yield of the hydroxide, how did this occur? It's because the definition of a base that we need to be familiar with now is based on the acceptance of a proton. Okay, so this NH3 here gets the acceptance of that proton from this H2O, which yields us to be able to have that hydroxide. You don't need to have a hydroxide in the actual reactants in order to have this yielded. If we look at a question like this, how do we solve this? Well, we have this, which is going to be our base, and it is a weak base, okay, so not all of it's going to be dissociated. Actually, only a small amount is going to be. So let's write this down, okay? We have our CH3NH2, and similar to up here, we're going to have our H2O. And what are we going to have it yielding? Well, this methylamine, it's going to become a substance that has an extra proton, right? So we're going to be putting a CH3NH3 instead of a CH3NH2, okay? Because again, it received that extra proton, okay? And then that means this H2O is going to now become the hydroxide, kind of similar to this one over here. And as you can see, we are ready to create our little ICE table, okay? So we're just going to be putting our ICEs over here. So it says in the question that we have 0.1 of our methylamine. Okay, so I'm going to be putting it here initially. All of these are going to remain constant for the water, similar to how we've been working with the acids, okay? But what does it say? Only 6.4% of this base has undergone ionization, which means that this value over here, we have to divide it by 100, okay? So that's going to give us 0.064, okay? So 0.064 of this value here is going to end up winding where? It's going to end up winding where our hydroxide concentration is going to be at the very end at equilibrium. So it's going to be somewhere down here. Now it's going to be mimicked with this one over here. So let's add this one here as well. And then we're just going to fill in our blanks. Okay, obviously initially we had none as our product, so we're just going to keep them as 0. We don't have a balanced chemical equation over here. We've kind of created a balanced chemical equation up here, and we can see that the coefficients are all a 1, so we'll just do a 1x. Okay, so this is going to be used up, so it's a negative x. These are going to be produced and gained, so these are a positive x. You just sum these all up, and this one here is obviously our x. This here is obviously our x. Now what can we do? Well, they're asking in the question for what is a Kb. Remember, this here is our base dissociation constant. So we're always going to have our products on the top, reactants on the bottom. So we're going to be putting this on top, CH3NH2, multiplied with our OH minus, all over our reactant, just our CH3NH2, our methylamine, and then we're just going to be putting all of our values and substituting them where they see fit. So we're going to have these multiplying together so that we can just square them, and then for here our reactant will just be putting our 0.1 subtracted by our x. We already have our x value, right? This here is our x, this here is also our x, so we're just going to be doing 0.1 minus that value of 6.4 times 10 to the negative 3. So just use your calculator. What do you end up getting? You end up getting a value of 4.4. I'm just going to round it to that, times 10 to the negative 4. Okay, so this here is our Kb value. Now, what is it asking for? Our pKb. Okay, so what is this pKb? Well, in short, it's pretty much a determination of the basic strength. And it's important to note that the lesser this value is, it's actually going to mean that the pKb is going to be a lot more potent, okay? So here, the lesser the value, the more potent the base is. I also want to add here that this is determining, I also want to add here, like I said, that it determines the basic strength. So it's also important to note that there is a particular formula for this. So for a pKb, it's pretty much this formula, negative log multiplied by the Kb. Okay, it's very similar to the formula for the pH and the pOH. Okay, we're just substituting this one over here with our Kb as opposed to the hydroxide or hydrogen ion concentration. So we're just going to get our value over Kb, which we found over here. What do you end up getting? A value of 3.36. This is your answer. Calculate the OH minus concentration and the pOH of that particular solution. Well, we give us that our Kb, or base dissociation constant, is 4.6 times 10 to the negative 4. What else do we need to do? Well, in order to calculate our hydroxide ion concentration, we should put an ice table. So let's write that out over here. And methylamine is going to be CH3NH2 over here. We have our H2O, and then of course it's going to be adding a proton, so it'll be CH3NH3, similar to the last question. Now let's input our values. Okay, so here initially we ended up having a value of 1.5. This all stays constant. This was 0, 0 in the beginning, and then of course technically we have our balanced chemical equation here. We can just put a negative x, we can put a positive x over here. They all have a coefficient of 1, and then you just sum them up. Now we have our Kb value, so we can actually write that over here, and we're just going to be putting them, our product on the top and our reactants on the bottom. Why are we doing this? So that we can eventually find the value of x. Once we find the value of x, we know that we've actually calculated our hydroxide ion concentration, because as we can see here, right, they are going to be equivalent. Next, after that, we're going to be using that hydroxide ion concentration that we have and plug it into our pOH formula in order to find our pOH. So our Kb value was 4.6 times 10 to the negative 4. It's equal to our x squared all over 1.5 minus x. Bring this all the way up here. So all we're going to do is expand. By cross multiplying in both directions, you end up getting 4.6 times 10 to the negative 4. Doing subfold method, multiplying all of these together, equaling x squared times 1 just gives us x squared. So what do we end up getting here to expand? You get 6.9 times 10 to the negative 4, negative 4.6 times 10 to the negative 4, x is equal to x squared. We're putting all of these over on this side, so our final equation ends up becoming getting this. Now we can just be putting this all into the quadratic formula. So this is our a, b, and c. Okay, so we have x is equal to minus b, plus or minus the radical, b squared, minus 4, a is going to be our 1 value here, c is going to be this value here. It's all going to be over 2 times 1, or 2a. If you do your little calculation here, you end up getting a value of x equals to negative 4.6 times 10 to the negative 4 plus or minus 0.05254 all over 2. Now we can put this, subject them into the positive route or the negative route. The positive route is going to end up becoming 0.02604 moles per liter. If we do it on this side for the negative, we end up getting 0.265, but it's going to be in a negative value. So obviously this wouldn't make sense. So we got to be using this one. So this here is our hydronium ion concentration, sorry, our hydroxide ion concentration as written here. Now we just got to do, we're doing our pOH formula. We're just going to be plugging in that value that we have up here. So this here is going to be our answer. We end up getting a value of 1.58. That's the answer. Well, let's have a look at this question over here. We're trying to calculate the pH. This is an interesting type of question because we're obviously going to be dealing with a base dissociation constant because we have Kb here, so we're dealing with a base in the solution. However, it does ask for pH, so we just do have to change it to a pH at the very end. Okay, so we have Kb is 1.3 times 10 to the negative 6. And then we have this as a concentration. Okay, so let's put our little ice table here like always. And then we can start putting in our reactants. We have our hydrogen. Over here, H2O gets dissolved. And then obviously this is going to become N2H5. Because it accepted that proton from this, and this ends up becoming OH minus. Now we're going to be putting our initial value. They say that it was 5.9 times 10 to the negative 2, again all in moles per liter. This is all constant. This one over here is going to end up 0. This one here is going to end up being 0 as well, because they are initial. And then from here we have to do our C, our changes. Again, we don't have a balanced chemical equation up here formally. Okay, so we can just be putting X, okay, our 1X as our change. Okay, and of course this was being consumed, so it has to be a negative, so it'll be a negative 1x. This one here is being produced, this one here is also being produced, so these will be positive x's. Okay, positive 1x. And then for E, obviously we know we got to be summing up our i's and c's together, so we get 5.9 times 10 to the negative 2 minus our x value. This stays down because it's just adding 0. Now we need to take a pause. What do we need to do? Okay, well, we obviously don't have our hydroxide ion concentration. This is going to be a problem because without our hydroxide, we can't be getting our hydrogen ion concentration in order to eventually get our pH for our hydrogen. So we obviously got to be able to find this. Okay, well, they give us that the Kb is this value. Okay, and we know that Kb is equal to our products on the top and reactants on the bottom. So our products end up becoming multiplied up here. And then our reactants is just our N2H4. So let's plug in our values. So our Kb is what, 1.3 times 10 to the negative 6. And then our products are just going to be x squared. And then this here just stays the same. Minusing x. Let's bring this all up here. Now we're going to be putting them and expanding it. What do we get? I get 7.67 times 10 to the negative 8. Minus 1.3 times 10 to the negative 6. X is equal to x squared. So now from here, I can put them all on this side over here, so we can have a nice quadratic formula equation format. So we have x squared now plus 1.3 times 10 to the negative 6x minus 7.67 times 10 to the negative 8 equal to 0. Let's put them all into our quadratic formula. X is equal to minus b plus or minus the radical b squared minus 4ac all over 2a. What do you end up getting when you do all of this? You're getting x is equal to negative 1.3 times 10 to the negative 6 plus or minus 5.53897 times 10 to the negative 4 all over 2. So again, this can be separated into two different routes, a positive route or a negative route. For a positive route, we end up getting 2.77 times 10 to the negative 4 is the moles per liter. For our negative, we end up getting negative 2.77 times 10 to the negative 4. Obviously this doesn't work, so we got to be obviously using this one over here. We're trying to find the pH, right? So we can right now use this to find our pOH at least, and we do that by using this formula. We just get whatever our hydroxide ion concentration that we got and insert it into there. We end up getting a value of 3.557. Again, this has to do with our pOH. We're trying to find the pH. Know that our formula for 14 was our pH plus our pOH. So in order to find our pH, we can just do our 14 minus our pOH. pH ends up becoming our 14 minus our 3.557. pH ends up becoming 10.44. That's the answer. These are our two green questions of the day. This here's the first one, this here's the second one. I also have a little chart here to help you out with any KB values that may help you answer either of these two questions. The base strength increases as you go up this chart. Okay, please try these on your own, and I'll be giving you the answers shortly. Pause the video. This is the answer to the first question. This is the answer to the second question.